Today we will be doing chemical kinetics. In a particular reaction, you know that the left-hand side components are the reactants and the right-hand side components are the products. Every reaction has a rate which is given by rate of disappearance of reactants, that is equal to, you can write it like this, minus 1 upon small a d of concentration of A by dt equal to minus 1 upon small b d of concentration of B by dt, and this is also equal to rate of appearance of products so that is equal to one by small c d of concentration of C by dt or 1 by small d d of concentration of D by dt. So the rate of any reaction is either you can say rate of disappearance of reactants, or you can say that it is rate of appearance of products. This is how we define rate of a reaction. Now, what are the factors affecting the rate of a reaction? What are the factors affecting the rate of a reaction? Suppose we talk about concentration. Definitely, if you have greater concentration of reactants, the rate of the reaction will be high. So, concentration of the reactants, definitely if the concentration of the reactants is more, the rate of the reaction will be more. So that is the point number one. So higher the concentration of the reactants, greater will be the rate of the reaction. Point number two is particle size. Now, you know that the more finely divided the particles, the greater will be the surface area. So, if you have smaller size particles, the surface area will be greater, and therefore the contact area will be greater, and therefore the rate of the reaction will be greater. So, the rate of a reaction increases with decrease in particle size. So this is point number two. The rate of a reaction increases with decrease in particle size. Point number three, physical state of the reactants. Now, based on the physical state of the reactants, we can classify the reaction as homogeneous or heterogeneous. Now, homogeneous means that the reactant molecules are uniformly distributed. Now, this is likely to happen if the reactants are either liquids or gases. Similarly, heterogeneous when the reactant molecules are not uniformly distributed. So, the rate of a reaction, it will be higher in this case. So, the rate of the reaction will be higher if the reactant molecules are uniformly distributed, or rather the reaction mixture is homogeneous. If the reaction mixture is heterogeneous, that means the reactant molecules are not uniformly distributed, then the rate will be lower. Generally, like I said, in case of liquids and gases, you can expect to get a homogeneous reaction mixture, and in that the rate will be higher. The next is temperature. Now, temperature is the most important factor. So, the rate of a reaction, it always increases with increase in temperature, but the mathematical calculation for temperature dependence is known as Arrhenius equation, and we will be discussing that later in this chapter. Next is point number 5, the nature of the reactants. Now, these are two reactions. Now, you will notice that these are two reactions. Nitric oxide with oxygen gives nitrogen dioxide. It's a very fast reaction. Carbon monoxide plus oxygen gives carbon dioxide. This is a slow reaction. So, the rate of the reaction also depends on the type of reactants. So, we can say that since you have to break two bonds over here, and rather the bond dissociation energy of carbon monoxide will be higher than the bond dissociation energy of nitric oxide, and that is why the second reaction is slower. So, the rate of the reaction depends on the nature of the reactants. Next is catalyst. The rate of a reaction increases by addition of catalyst. So, a promoter increases the activity of a catalyst, and inhibitor decreases the activity of a catalyst. Right, so a promoter increases the activity of a catalyst and an inhibitor decreases the activity of a catalyst. So these are by and large the 6 important factors affecting the rate of a reaction. Now consider this particular reaction, 2NO2 plus F2 is equal to 2NO2F. Now in this reaction, initially the scientists thought that the rate of the reaction is proportional to the molar concentration of N2 and F2, each raised to the power equal to stoichiometric coefficient. So initially there was a belief that the rate of the reaction is proportional to concentration of NO2 whole square into concentration of F2, and the constant of proportionality, that is K, is called the rate constant of the reaction. So K is called the rate constant of the reaction. Now the thing is कि this particular formula was known as law of mass action. So although law of mass action was very easy to comprehend because everything is based on the stoichiometric coefficient, which can be easily found. However, on analysis it was found that the rate dependence is not on concentration of NO2 square, but it is only on concentration of NO2, and this formula was known as rate law. So according to scientific theory, the law of mass action appears to be theoretically correct, but in practice we determine the exponents experimentally. So by experiments in the laboratory, we determine the exponents which are to be put for each concentration, and the final equation is known as the rate law. So the rate of the reaction is equal to rate constant times concentration of NO2 to the power 1 into concentration of F2 to the power 1, and these exponents, like I said, are determined experimentally. Now the exponent of NO2 is 1 and the exponent of F2 is 1. The total exponent is 2, and this is known as the order of the reaction. So the order of the reaction is basically the sum of the exponents to which the molar concentrations are raised in the rate law. That is the definition of order of a reaction. Now let us discuss a couple of first order reactions. There is a reaction H2 plus Cl2 is equal to HCl. H2 plus Cl2 is equal to HCl. Now the thing is, this reaction this is a zero order reaction, this is a zero order reaction. So in this reaction it was found that the rate law is equal to K into concentration of H2 to the power 0 into concentration of Cl2 to the power 0. So the rate dependence on concentration of H2 and Cl2 is 0. Now why does this happen? It happens because the mixture of H2 and Cl2 is taken over water in a closed tube, right? This mixture of H2 and Cl2 is taken over water in a closed tube. So what happens is that as soon as HCl gas is formed, it starts dissolving in the water. As it dissolves in the water level rises, so the volume available to the gas comes down, and even though the moles of H2 and Cl2 is decreasing, the volume is also decreasing, and therefore the concentration of H2 and Cl2 remains constant. So that is the reason why it is a zero order reaction. So once again, the mixture of H2 and Cl2 is taken over water in a closed tube. As HCl is formed, it dissolves in the water, so the water level keeps rising, so the available volume keeps on decreasing. So even though the number of moles of H2 and Cl2 is decreasing, the molar concentration does not change, and therefore it is a zero order reaction. Now the thing is that consider the dissociation of ammonia under the influence of heat to nitrogen and hydrogen. We use catalysts like molybdenum or tungsten. Now the thing is that when you have a catalyst like molybdenum or tungsten, the catalyst provides a surface on which ammonia molecules get adsorbed. So the catalyst tungsten basically provides a surface on which ammonia molecules can get adsorbed. Now the thing is that when the ammonia molecules get adsorbed, then we can allow heat to dissociate them into nitrogen and hydrogen. So the adsorption slows down the ammonia gas molecules, and therefore it is possible to apply heat and dissociate ammonia into nitrogen and hydrogen. Otherwise, ammonia being a gas, it may be difficult to perform this dissociation unless we can control the movement of the molecules. So in this manner, in a very short span of time, the entire surface of the catalyst is adsorbed by ammonia, and thereafter the concentration of ammonia does not affect the rate of the reaction. So that is why it is a zero order reaction. So this is the rate law for the dissociation of ammonia. Suppose there is a reaction in which R is the reactant and it's giving some products. So we can write the rate law like this. After that, you can cross multiply and write like this. And the next reaction will be this. At time t equal to 0, the concentration of R will, let us call it as R naught. So therefore we can say that C is equal to R naught. So this gives concentration of R equal to minus kT plus R naught. Therefore Kt is equal to R naught minus R. So the thing is, this is how we can find out the rate constant of a zero order reaction. So this is the formula which enables us to find the rate constant of a zero order reaction. Now one important thing you will notice that the unit of rate constant, it will be moles per liter second. The unit of rate constant will be moles per liter second. Another thing is that there is a concept called half-life. So the concentration of R naught, that is initial concentration, minus half R naught by T is equal to K. So we are getting the half-life formula for any zero order reaction. This is the formula. So you can write this as T half. So T half is the half-life and it is equal to concentration R naught divided by 2K. So this is the topic zero order kinetics. Now we come to first order kinetics. Suppose you have a reaction like this. A reactant is giving products, so d of concentration of R by dt is minus k into concentration of R to the power 1. So we can write the reaction in this form. After that, you integrate both sides. So you will get log of concentration of R to the base E equal to minus Kt plus C. Now when time is 0, the concentration can be written as concentration of R0 so we will get integration constant is log R0 by E. So log of concentration of R equal to minus Kt plus log R0. So we will get Kt is equal to log concentration of R0 by concentration of R to the base E. So you can say that the rate constant is 1 by T log concentration of R0 by concentration of R to the base E, and instead of log base E, if we prefer to take log base 10, then this is the corresponding formula. K is equal to 2.303 by T log concentration of R0 by concentration of R to the base 10. Now you can easily see that the unit of rate constant will be per second because it is inversely proportional to time. And once again, like we did for zero order, if we now analyze the half-life, so analysis of half-life basically tells us that log concentration of R0 by half R0 base 10 so 2.303 by K log 2 base 10. So T half is 0.693 divided by K because log 2 base 10 is approximately 0.3, so that multiplied by 2.303 is approximately 0.693. So this is the formula to find the half-life of a first order reaction. Now there are a lot of numericals where they talk about 2 half-lives or 3 half-lives, so just keep it in mind that if it is 1 half-life, then the concentration becomes this much. If it is 2 half-lives, then the concentration becomes half of this, that is concentration of R naught by 4. Similarly, if it is 3 half-lives, that means the concentration becomes box R naught by 8. So there are a lot of numericals and questions where it is mentioned 2 half-lives or 3 half-lives. That time you have to take the concentration like this. Now in a first order reaction, there are certain cases where the reactants and products are all gases. Let's have a look at a reaction like this. In this particular reaction, A, B, C are all gaseous. So in such reactions, we prefer to use partial pressure. So suppose, let us say Pi is the initial pressure that is due to A, and after some time, that is let us say after a time t, it is Pi minus x, x and x. So the total pressure at time t will be given as by the total of these three. So the total of these three is coming to Pi plus x. So this is the total pressure. So x will be total pressure minus Pi. In the meantime, the partial pressure due to A is Pi minus x. So in this formula, you replace the value of x, so you will get 2 Pi minus Pt. So the rate constant is 2.303 by T log Pi by Pa. So we can also write it as 2.303 by T log Pi divided by 2 Pi minus Pt. So if the reactants and products are all gaseous, in that case it is better to follow this particular method, that write everything in terms of the partial pressure, and the important terms will be initial pressure, which will be only due to A, and of course the total pressure at any time T, which will be due to all the gases A, B and C. So this is how we can do the first order kinetics of a gaseous reaction mixture. Now the thing is, during the discussion about rate law, we had said that these exponents are determined experimentally. So just to give you an idea how it is done, suppose there is a reaction A plus B. Suppose there is a reaction A plus B is equal to products. Let's say this is the reaction. Now in this reaction, what we will do is we will record the concentration of A and B, and we will do it 3 times. So we are basically doing 3 experiments. So, and let us say that these are the recorded values. So these are the recorded values. So we have in the first experiment concentration of A, concentration of B, rate of reaction, and again same way for second experiment and third experiment. Now we do not know what is the rate law. So what we will do is we will write one arbitrary equation, concentration of A to the power x into concentration of B to the power y. So if the rate of the reaction is 4.2 into 10 to the power minus 6, so that is K into 1 to the power x into 0.15 to the power y. If the rate is 8.4 into 10 to the power minus 6, then this will be the equation. If the rate is 5.6 into 10 to the power minus 6, then this will be the equation. So these are the 3 equations. And now what we will do is that if you call these 3 equations as equation 1, 2 and 3, so if you divide number 2 by number 1, you will get 2 is equal to 2 to the power x. So x will be 1. And similarly, if you divide number 3 by number 1, then this is what you will get. So y will be equal to 1. So you can see how we have managed to get the exponents x and y by making use of these experimental values. So this gives you an idea how the rate law is determined experimentally. Now we come to the next topic, that is molecularity of a reaction. The next topic is molecularity of a reaction. A little while ago during the chapter, we had a look at this particular reaction, 2NO2 plus F2 is equal to 2NO2F. Now you may recall that in this reaction, the rate is equal to K into concentration of NO2 into concentration of F2. Why is the rate law like this? What is the reason behind it? Actually, this reaction is a multi-step reaction. So there is a slow step, that is this, and there is a fast step, that is this. So there is a slow step and there is a fast step. So in the slow step, actually what happens is that fluorine molecule gets converted into atomic fluorine. An atomic fluorine which is highly reactive attacks NO2 in a very fast step to give NO2F. Now, according to the theories of chemical kinetics, the rate of a reaction is always determined by the slow step. So, in the slow step, you will see that the stoichiometric coefficients of both NO2 and F2 are 1, and that is the reason why the rate of the reaction is equal to rate constant times NO2 to the power 1 into F2 to the power 1. So, if you are asked the order of this reaction, the order will be 2, because in the slow step the stoichiometric coefficients are 1 and 1, so the order will be 2. Now the thing is that in this reaction, each step has its own molecularity. Now molecularity is nothing but the total number of moles of reactants in a particular step. So the molecularity of this step will be 2, and the molecularity of this step will also be 2. So this is a very important thing, that the molecularity of a particular reaction is nothing but the number of molecules or ions which are taking part in that particular step. So when you say molecularity, it is for each step, but when you say order, then it is for the slowest step only. So we will only consider the slow step, and that will determine the order, whereas molecularity is to be written for each step separately. So that is the molecularity of a reaction. Now there is a very important reaction known as hydrolysis of ester. So there is a very important reaction known as hydrolysis of ester. This is an ester. On hydrolysis, it gives acid plus alcohol. Now, in this reaction, the mixture is considered to be in excess. The water is considered to be in excess. So what happens is that the rate of the reaction is found to depend on concentration of ester to the power 1. So that means that it is a first order reaction. However, the reason why the reaction is first order is because we are considering that water to be in excess. Now suppose the same reaction, if water is added drop wise to the ester, suppose water is added drop wise to the ester, in that case the rate law will become like this. So if water is added drop wise to the ester, the rate law will be rate constant into concentration of ester into concentration of water. And otherwise, when water is considered to be in excess, then the rate law will be rate constant into concentration of ester. So this kind of a reaction is called a pseudo first order reaction. So in a pseudo first order reaction, it appears that the order should be 2, but because one of the two reactants is in excess quantity, its concentration will not affect the rate of the reaction, and such reactions are known as pseudo first order reactions. Now, there was a talk about factors affecting rate of the reaction, and we had discussed that temperature plays a very important role. What happens is that normally in a reaction like H2 plus I2 equal to 2HI, you have H2 and I2 reacting with each other to give an intermediate like this. So H2 and I2 react with each other to give an intermediate. So this intermediate is known as activated complex. This activated complex has got very high potential energy. So the potential energy of the activated complex is so high that it is unstable, and therefore it ultimately dissociates to give the products. Now if you try to graph the energy of reactants and products, then this is how the graph will look. This point is A, this point is C, this point is B. Now C corresponds to activated complex, and A corresponds to reactants, and B corresponds to products. So the reactants have a certain amount of energy, and the activated complex has a considerably higher amount of energy, and finally it dissociates to give the products. Now the thing is, the difference of energy between the reactants and the products is delta H. So delta H is what we call the enthalpy of the reaction. Now the difference of energy between the reactants and the activated complex is known as activation energy. So activation energy is the minimum energy which the reactant molecules must have in order to achieve the transition state, and subsequent to that they will certainly yield the products. Now there is an important graph, because now we have understood that the reactant molecules must acquire activation energy for a successful reaction. So there is a graph. In this graph, the y-axis is fraction of molecules, and x-axis is kinetic energy of the molecules. The peak of the graph is known as most probable kinetic energy, right? So the y-axis is fraction of molecules, x-axis is kinetic energy, and the peak of the graph is most probable kinetic energy. Now, in such a graph, you will find that there will be a barrier like this, and only when you are to the right side of this barrier represents activation energy. So only those molecules which are on the right side of this barrier, they are the ones which are capable of effective reaction, because they can acquire activation energy, or they possess that much energy to have a successful reaction. Now the thing is, the temperature dependence can be shown by means of a graph like this. See, there are two different graphs. Suppose this graph is for temperature T, and this lower graph is for temperature T plus 10. So as usual, this is the energy barrier, and those molecules which are on the right side of this, they are the one which can have effective collisions. So you will notice one thing, that at temperature T, these are the molecules which have enough energy to cause effective reaction, and at temperature T plus 10, these are the extra molecules which have the energy to cause a successful reaction. That means at the higher temperature, the fraction of molecules which is capable of effective reaction is greater. So this graph clearly tells us the impact of temperature on the success of a reaction. So this brings us to Arrhenius equation. So this brings us to our next topic, that is Arrhenius equation. According to Arrhenius, the rate constant of any reaction is equal to capital A. Now the thing is that capital A is known as frequency factor. So capital A is known as frequency factor. Capital A basically gives us the frequency of collisions and into e to the power minus activation energy by RT. So the thing is that you can easily see from this that if the temperature is higher, the rate will be more. So Arrhenius equation basically says that the rate constant is frequency factor. Frequency factor is a measure of the frequency of collisions into e to the power minus activation energy divided by RT. So this is a very, very important equation to understand the temperature dependence on the rate of a reaction. Now, in its original form, the Arrhenius equation is a little cumbersome, so there is an alternative form where you can take log on both sides. So if you take log on both sides, you will get log K is equal to log A minus EA by RT. Now suppose the temperature is T1 and at that temperature the rate constant is K1. Suppose the temperature is T2 and at that temperature the rate constant is K2. So if you subtract these two reactions, you will get log K2 by K1 is equal to activation energy by R into 1 by T1 minus 1 by T2. So this is a very, very useful formula to find the activation energy of any reaction. Suppose we know at temperature T1 what is the rate constant, at temperature T2 what is the rate constant, then we can find out the activation energy by using this reaction. Now, Arrhenius equation was found to be pretty authentic because it takes into account the two most important things. One is activation energy and one is frequency factor. And the theory which led to the formation of this equation is known as collision theory. Now, collision theory basically says that all the reactant molecules are rigid hard spheres, and therefore when they have collisions, the activation energy apart, the frequency factor also plays a role. So that is the theory which led to the formation of this particular equation. Now the thing is, one demerit of the collision theory is that it does not take into account the orientation of the molecules. Like say for example, this is a very well-known SN2 reaction of organic chemistry. This is a very, very well-known SN2 reaction of organic chemistry. Now in this reaction, if OH minus attacks from the right side, then the reaction will be unsuccessful. But if OH minus attacks from the left, if OH minus attacks from the left, then the reaction will be a very successful SN2 mechanism. So the collision theory does not take into account the orientation of the molecules, and therefore perhaps the correct equation should be rate constant equal to this particular term should be present, and this term is known as steric factor. So the rate constant is equal to steric factor into capital A to the power capital A into e to the power minus EA by RT. So with the inclusion of steric factor, the equation becomes correct. So that it brings us to an end of Arrhenius equation, and it also brings us to an end of this particular session of chemical kinetics.